The title of the lab is to obtain the step response for the transfer function and state space representation in Simulink. Similarly, we will solve a solution of differential equation in Simulink. We will design a PID controller, and similarly, if you are having a lag-led compensator, how we can design the lag-led compensator in Simulink. So the first lab task is just you can study different types of the system. You are having over-damped system, you are having the critical damped system, under-damped system, and the factor that is we will study that is changing is the zeta damping ratio and the undamped natural frequency. So if the system is overdamped, the zeta, the damping ratio is greater than 1. If the system is underdamped, so the zeta is less than 0, greater than 0, and less than 1. Similarly, for the critical damped system, we are having zeta that is equal to 1. Okay. And we are having some other system, for example, non-minimum phase system. That is important, how it looks like, and the step response in Simulink using the transfer function. So starting the MATLAB Simulink, here is a Simulink library. You people can see it here. Let me click on the Simulink library. Now it's taking some time. Okay, we are having the Simulink library browser that is loaded here. There are some commonly used blocks. You people can see here by just clicking on these blocks. Okay, so here is the icon that is for the new model. So let me load a new model. You people just can play with this. I'm just clicking here on the sources. So in the sources, you can see here the clock, the constant term, similarly the ramp input. We are having some other signal, sine wave, step input. Similarly, you can on the sinks, you can see here the display, the floating scope, the scope, on which the plots are there are plots here on the scope. We can display it on the scope. Similarly, some other signal routing attributes, so you may just have a look into it. Well, this is the new model. So let me start the first lab task, which is the overdamped system. So for this purpose, I have to click inside the untitled Simulink new model. Here you can just write STEP step, enter. So there will be step input. So this is here is a step input. Similarly, you can write transfer. So here the transfer function. Just enter. And the scope, SCOPE, scope. So enter the scope. Scope will appear. And this is the Simulink. Simulink is GUI based. This is graphical user interface. You can see the blocks where command prompt is command based. Similarly, you are having another window that is editor window, and the third type of the window is the Simulink, which is the GUI based. So let me connect all these. Inside the step, you can change the value as well. This is step time. The initial time starts from 0. The final value of the time will be 1. Similarly, you can change the value of the transfer function. The coefficient of the numerators are, let's say this is the 9, and we are having a system 1, 2, and 9. Okay. Which type of the system this is? This is under dam system. So let me change it to the over dam by writing 9, the coefficient here to 9, coefficient of 2, replacing 2 by 9. Okay. Now here you can simulate the system without saving the same system. You can just simulate over here. By clicking on the run. So here is the response. So this is the response. You may click on the auto scale. So this is the step response of this is the ORDM system. That is starting from 0 and the final value of the response that is equal to 1. And you people know that they are having this is second order system. So the ORDM system is having 2 poles, and these poles are at the negative side of the complex plane. And if you people can solve it, so there is a exponential to the power minus, there कोई value होगी, and that decays before वो जो exponential आपको पता है कि अगर negative side पे real axis पे आपके कोई आ जाता है exponential to the power minus, तो वो जल्दी decay कर जाता है. और हमारे पास जो transient response होगा वो smooth response होगा. Okay, let me change it to the critically damped system. We are having 6 over here, and let me execute the program. So this is the critically damped system. Now if I'm interested to make difference between overdam system and the critically damped system, so I need another transfer function. It would be composite transfer function. Let me connect this to over here. I will require a mux multiplexer. Just I'm MUX mux, enter. Here is the multiplexer. You may change the values of the input as well. So if you require more than 2 inputs, so you can just write over here. If people require 3 inputs, so just write 3 over here. Okay. Let me change the coefficient of the numerator, that is 9, and the coefficient of denominator 1, 9, and 9. I'm executing the program. Here you can see, you can make difference. You can differentiate between the 2 responses here. The purple color response This is the overdamped system. This is a bit sluggish response. And you people can see here the yellow response, that is the critically damped response. Okay, proceeding further, let me change the value to here 2. Let me write over here 2, the coefficient denominator in the first transfer function. Auto scale. Now, the yellow response, yellow color response is the underdamped response, and the purple is the overdamped response. So you can differentiate between two responses as well here. जहाँ जिस तरह आप उसमें वहाँ पे कर सकते हैं एडिटर में और कमांड प्रॉम्प्ट में सब जो मल्टीपल प्लॉट्स थे एक विंडो में एक फिगर में करा सकते थे प्लॉट कमांड के थ्रू. ओके, now if you're having a transfer function of the antenna is a mute position control system, that is in your book, Norman S. Nice, control system engineering book written by Norman S. Nice. It's a very authentic book. One of the examples that is discussed throughout all the chapters, that is antenna as a mute position control system, where the input is again the input is the position, so some theta I, and the output is the position of the DC motor, and that is that can give, so that is similar what we have discussed in the lab number 8. In lab number 8, we give a square wave to the DC motor. The DC motor can give the output response by emulating the input square wave. And the antenna as a mute position control system, जो आप इसको input required set point देते हैं, वो उसको follow करता है. And that is one of the excellency of this servo system. कि this is the mark attributes कि servo सिस्टम में आप सिंपल डीसी मोटर को 1 डिग्री तक रोटेट करा सकते हैं, पोजीशन को आप उसकी पोजीशन को चेंज करा सकते हैं, कंट्रोल कर सकते हैं of the DC motor. Okay, so we are having this is the transfer function for the antenna. The 3 blocks we have studied. The first block was the preamplifier as the power amplifier. The second block was, you people know that it was the motor and the associated load. And the third block was the differentiator. So this is the resulted 20.83 in the numerator. Similarly, here this value is 101.71, and the third coefficient is 171. Okay. This is how it looks. This is the response, and you can see here the response settles at 0.12, and here is a large steady state error. Input is the step input. They are having a step input provided to the system, and the response is, you can see here, is up to 0.12. It should reach to 1, and there is a large steady state error. So if you people can write it manually, you people can understand this. कि जब आप इसको मैनुअली सॉल्व करते हैं तो आपको पता चल जाएगा कि जो फर्स्ट रिस्पांस आएगा उसमें उसका एम्पलीट्यूड होगा 0.12 एक्सपोनेंशियल टू द पावर माइनस समथिंग होगा. दैट इज गिवन इन द बुक एज वेल, जो मैंने आपके साथ शेयर की है लैब 7, 6 और 7, इसमें भी है. ओके, सो दिस इज हाउ यू कैन the step response, you can implement it in the Simulink. Similarly, how we can represent, we're having the same system, and that system, we are having the open loop transfer function g of s that is given here. And if this transfer function is converted to the state space form, so that this is the state space representation. And you people also know that the state space representation is not unique. ये unique नहीं होता. किसी भी transfer function के infinite solutions हो सकते हैं. आपको एक form में या दूसरे form में नजर आ सकते हैं. So the state space representation of the transfer function is not unique. Okay. So these are the coefficient of the system matrix A, which is very important. Similarly, we are having this is the matrix, the vector, the column vector B, and this is the row vector C, the output matrix C. So how it looks like in MATLAB Simulink. So you can just click here and write state space. So here is a state space representation, state space block. This is state transition table. Let me delete this one. State. The first one is the state space. This is the state space block. Let me delete this one. Let me enlarge the model so you might have seen it. I'm putting the coefficient of state matrix A, square brackets, minus 101.71. The second coefficient is minus 100, semicolon. 2 cross 2 matrix, the order of the matrix 2 cross 2. Second row start with 1, and the next coefficient, the next element is 0. Similarly, B matrix, which is a column vector, 1 followed by 0, and the transpose of the matrix B, apostrophe. Similarly, matrix C, input matrix C, that is 0, 20.83, and the D matrix that is equal to 0. Okay, let me simulate the system. This is the response. The same response we are having, just like in the transfer function case. So this is the response and the state space. Okay. Here, we are having a differential equation with some initial condition. And this is the state space representation of the differential equation. The order of the differential equation is third order differential equation, linear differential equation with some initial conditions. Initial conditions y0 is equal to 2, y dot 0, 1, y double dot 0, that equals 0.5. And that is the state space representation. Third order system is 3 cross 3. System matrix A is 3 cross 3. Similarly, the B matrix, in this case, the forcing function is 0. And we are having 1 cross 3, that is the C matrix. So with some initial value here, 2, 1, 0.5. These are the initial values. So just you can change these values. That is 0, 1, 0, semicolon, 0, 0, 1, semicolon, coefficient minus 10, minus 17, and minus 8. Minus 10, minus 17, minus 8. Fine. B matrix is 0, square brackets, 0, semicolon, not 0, 0, 0, 0, and the transpose of the matrix. C matrix is 1, 0, 0. And we are having the D matrix is the D value of the D matrix is 0. Similarly, the initial conditions are here. These are the initial conditions. The square brackets 2, 0.5, 2 is followed by 1, and then 0.5. And this is also a column vector. So let me write the apostrophe, the transpose of the matrix of the initial values. Okay. So you can see the response here. Yes, this is the response. So if you are having a system and that is represented by the differential equation, and if all the values are the initial values are 0, and we provided a step input, जब हम उनको स्टेप इनपुट देंगे तो जो रिस्पांस होगा, आउटपुट रिस्पांस क्या हो जाएगा, वो 0 से स्टार्ट होगा. आउटपुट रिस्पांस या जो सिस्टम का रिस्पांस होगा वो इमुलेट करेगा स्टेप रिस्पांस को, जो आपने उसको इनपुट रिस्पांस दिया है. वो अगर इन द फॉर्म ऑफ स्टेप रिस्पांस हो, यूनिट रैंप हो, यूनिट पैराबोला हो, साइन वेव हो, कॉस वेव हो, तो उसको इमुलेट करेगा, इसको फॉलो करेगा. In this case, we are applying step input as a step as the input, and we are having some initial condition of the differential equation, that is y0 is equal to 2, y0 is equal to 0.5, 0.5, and then 1. So the system is approaching to 0, the natural response is approaching 0, right? We are having a stable system here. So अगर किसी सिस्टम के अंदर एनर्जी पहले से स्टोर्ड हो, फॉर एग्जांपल मैकेनिकल से, वी आर हैविंग मैकेनिकल सिस्टम, मास, इनर्शिया, विस्कस टेम्पर, अगर उसकी स्प्रिंग कांस्टेंट्स वगैरह हो, इनिशियली कुछ वैल्यू हो, तो वो 0 से स्टार्ट नहीं लेगा. सिमिलरली वी आर हैविंग इलेक्ट्रिकल सिस्टम, इंडक्टर, कैपेसिटर्स, इफ देयर इज सम एनर्जी स्टोर्ड, सो द रिस्पांस जो होगा वो 0 से स्टार्ट नहीं होगा, बल्कि सम इनिशियल वैल्यू पे डिपेंड करता है. ओके. Here we may solve the differential equation as well. We can solve this differential equation in Simulink as well. Alternatively, Control C, in notation, Control V. This is the transfer function, and if we people are interested to solve this differential equation, what is the response? So we may have the representation in Simulink. For example, we are having this differential equation, y triple dot plus 8y double dot plus 17y dot plus 10y, that is equal to 0. So the B matrix or the forcing function in this case is equal to 0. And we are also supposing here that all the condition here, initial conditions are assumed as 0. So, okay, how to solve this? We will let the y triple dot on the left hand side, and the rest of the rest of the variables with the lowest degree will be shifted to the right hand side of the equation. So it will be minus 8y, it will be 8y double dot minus 17y dot minus 10y. Similarly, if we people, these are derivatives of order 3. So if we can integrate this 3 times, if we required y, simple y, output y response, so we will differentiate this y triple dot. We will not differentiate, we will integrate this derivative 3 times. Similarly, here 8y double dot, so we will integrate y triple dot only once. Here, in the case of 17y dot, we will integrate y triple dot signal twicely. यहाँ पे इसको, और सिमिलरली यहाँ पे हम इसको 3 times यहाँ पे इसको integrate करेंगे. So how it looks, we will require a sum SUM that is followed by GAN gain. Click on the gain, Control I, it will be flipped here. Controls, click on the gain, Control C, and then here Control V and Control V. Similarly, for integration, click here, INTEG, integrator. Enter. So here the integrator will appear. Click on the integrator, Control C, Control V, Control V. Okay. By default, there are only 2 inputs and 1 output of the summer, so I can change it over here. Instead, the first is plus, and the rest of the signals will be negative. So 1, 2, 3 signals. Output is connected to the first integrator. So after the first integration, what is the coefficient of 8y double dot? That is equal to 8. So let me write, click on it and enter 8. Okay, that is provided to the here. This is negative minus 8. Similarly, the second coefficient is minus 17. Just write 7. Okay. And the third is 10y. And output of is applied here. Okay, what is the gain of that is 10. Okay, let me apply the step input as well. So this is how it looks like. Let me execute differential equation. So this is the response, that is starting here from 0 and up to going to the 0.1. That this is the response with some initial conditions. That is okay. We can simply write this one all the coefficient of these the differential equation. If this is converted to the S domain and that is converted to the Laplace transform to the transfer function, and simply we can write here the transfer function with step input and the scope as output, and you can implement this whole circuit. अगर हमारे पास यहाँ पे डिफरेंशियल इक्वेशन गिवन हो और वो टाइम डोमेन में हो तो हम इसको इस तरह इम्प्लीमेंट कर सकते हैं. अगर इसी डिफरेंशियल इक्वेशन को हम इस डोमेन में या ट्रांसफर फंक्शन में चेंज कराते हैं वो फिर काफ़ी आसान हो जाता है. जस्ट वी हैव टू वी विल रिक्वायर द ट्रांसफर फंक्शन हियर. ओके, गोइंग फर्दर, the design of the PID controller in Simulink. This is the design of the, so let me open a new model. This is a new model. You will require the step. Similarly, we will require the summer. Okay. And derivative. This is the derivative term plus gain term. So the gain term and integrator. So this is the integrator. Step is input is applied to the summer. Output is connected here to the gain. Similarly, this is the difference. Signal is provided to the derivative, to the differentiator circuit. And here again we will require a summer. This is a summer. And we will require another plus as well here. And followed by the transfer function. That is the transfer function. And the scope. This is the scope. Now let me change the value of the transfer function. What is the coefficient of the coefficient in the numerator? These are 20, 1, 9, 11, 20. 20, 1, 9, 11 or 20. 1, 9, 11, 20. Okay, fine. Similarly, we will require the values the KD here. So I will require the gain, That is the potentiometer values. Similarly, I requires the KI terms. This is the KI term. Okay. So what are the values of coefficient of the gain? 200. Gain of this is equal to 1. What is the value of the gain value? Kp is equal to 200. Kd 170. $200, 170. What is the value of the Ki term? The coefficient, these are the constant terms. 10. Okay. Let me put a feedback as well. And that feedback should be negative. एग्जैक्टली इसी तरीके से हमने इसको इम्प्लीमेंट किया है जो हमारे पास जो लैब नंबर 8 है जिसमें आपको बताया था feedback is here is negative, so let me change the sign to the negative. This hole is the PID controller जो पैरेलल में लगे हुए हैं, ब्लॉक्स पैरेलल में लगे हुए हैं. Well, we also may have the PID controller that के ये सारे जो ब्लॉक्स कैस्केड में लगे हुए हो. This is the transfer function of the process. Just like in this case, अगर हमारे पास of the plant, this is the plant. So this plant might be in electric engineering. This plant might be the DC motor. This might be the transfer function of the system. Okay, so we are simulating the system, and we can see CO. So you can see here, the system is highly unstable. The overshoots, there are oscillations, and these are the growing oscillations. So it means that this system is unstable system.